Good morning. This recording is for Algebra 1, Chapter 9, Lesson 1, Exploring Quadratic Graphs. All right, so quadratic, it makes you think of 4, right? Well, it shouldn't make you think of a 4-term polynomial. It should make you think of a square, because squares have 4 sides. So quadratic means square or squared, like to the second power. So that's what quadratic means, something to the second power, okay? And you're going to be graphing a lot. You're probably going to have to make quite a few tables. You're going to probably want to use GraphSciCal. Yeah, okay. So let's go ahead and take a look at some quadratic functions, all right? Function just means basically it's got an x and a y, or an x and an f of x. But again, f of x is just a fancy way of saying y, all right? Now, I have 3 different graphs here. I have the red one, the blue one, and the green one. And the red one is the one in the middle. And the blue one's the narrowest one. And the green one is the widest one. Now, as you can see, the blue one, which is the narrowest one, has a 3 in front of it. And it's going to be really hard to make that bigger, but it's got a 3, all right? It's 3x. Whereas the red one is just a 1x, and the green one has a 1/3 x, all right? So that's going to kind of lead us to some principles about quadratic graphs, all right? And so some things that all the graphs have alike is that they all go through 0, 0. All of them have what we call a vertex of 0, 0, and the vertex is where the parabola, which is actually what a quadratic graph is called because it's U-shaped. A parabola is U-shaped. And so all of these graphs kind of make a U-turn at the same vertex. So the vertex is the point where the parabola makes the U-turn, where it goes to turn around and go back the way it came, and it goes back. Okay? So all of them go through 0, 0. All of them are U-shaped, parabola-shaped, and all have an upward opening. They all open upward, okay? Now, the blue one, again, is the narrowest, the red one's the middle, and the green one is the widest. There we go, all right? And again, the difference in the widths is what are all different about each one, even though all of them go through the same vertex. All of them have an upward opening, and of course, all of them are U-shaped. So, if I were to just graph the most simplest of them, and that was y equals x squared, which was that one. It was also the red one. And I did -2 as x. I'm going to get -2 to the second power, which is -2, 4, which is that dot right there. 0 to the second power, which is 0, 0, which is that dot. And 2 to the second power, which is 2, 4, which is that dot. And again, you can see how it would be U-shaped if I were to kind of connect the dots and keep going. Right there. Okay. You guys getting the idea? Okay, good. All right, so we're leaving the land of the linear and into the land of the curved. All right, we're going to be talking about parabolas, U-shaped graphs. All right, so the standard form for the quadratic function is y equals ax squared plus bx plus c. And if I were to write this without the caret, it would look like this. Because remember, this little caret thing means to the second power, or just to the. All right, so some examples of quadratic functions would be y equals 5x squared, y equals x squared plus 7, and y equals x squared minus x plus 3. All right, so as you can see, this first one only has the first term. This one, the second one, has the first term and the third term. And the last one has all 3 of them. Okay, so there we go. All right, so quadratic parent function, and that's the simplest. The simplest function is f of x equals x squared, or again, y equals x squared. All right, so again, that would be f of x equals x squared, or y equals x squared, because just remember, f of x is a fancy way of saying y. All right, quadratic functions are U-shaped when graphed, a curved graph, or a curve called a parabola, okay? So it's U-shaped, and that U-shapedness is what we call a parabola. Parabolas are symmetrical. That means if you fold one side onto the other side, the sides are going to line up, much like a t-shirt. Okay? The line that you can fold a parabola in half on is called the axis of symmetry. It's the point where you fold it over. The point of the parabola that lies on the axis of symmetry, either the highest or lowest point, is called the vertex. All right? And again, I've talked about that in the last slide, but there you go. Those are the definitions. All right. So, too far. Let's see here. There we go. All right. Okay. So, standard form of the quadratic function, again, is ax to the second plus bx plus c. And if a, again, a right there, is greater than 0, so positive, if we have a positive a in a quadratic function, then the parabola opens upward. If a is negative or less than 0, the quadratic function, the parabola opens downward and the vertex is the maximum, okay? So if you were to look at this highlight that I have here, if you got this highlight that I've got here, right there, it's opening downward, which means the number in front of x must be negative. In this case, it was -3, all right? So this graph right here represents this right there, okay? So that would be the -3 affecting the equation, affecting how the graph is forming. Whereas this one over here that opens upward has a +3 as its a, which means it's going to affect the fact that the parabola opens upward. Okay, let's move on. So let's go ahead and identify the vertex and state whether it is a minimum or a maximum. I'm going to do a little bit more than that just to remind you from previous lessons what's going on here and how you can define things, because you should know already how to do it, but this will be a little bit of a reminder. So let's go ahead and take a look at the first graph on the left. It has a vertex with the highest point of 4, 3, which means it's a maximum. It means the whole parabola takes place less than 3, which means you could say the domain is all real numbers, because really, if you think about it, this line's going to go on forever and ever 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 and past my iPad and past this recording, and it's just going to end up being all the x's it possibly could, which is why the domain, which is the x, is all real numbers. The range, on the other hand, is basically that blue line right there that I drew. Nothing takes place on the y-axis past that line, which means we state that the range is less than 3. Okay? And we could also say that the axis of symmetry, which is right there, is 4. And it means that all of the points on my parabola are equidistant from the one on the opposite side of the axis of symmetry. Okay, they're all equidistant. You guys seeing that? I'm kind of writing all over myself. It's getting a little messy, but you get it, right? The axis of symmetry. That's the point where if I took the left side of the parabola and folded it over on that line, it would match up exactly with the stuff on the right side of that line. Okay, so let's take a look at the next one. The vertex is -3, -3. It's a minimum because it's the lowest point of the parabola, and lowest, minimum. Yeah, makes sense. All right, domain, still all real numbers because, again, this could go on forever, and this side could go on forever, even past my iPad, past the recording. It's going to be all real numbers, right, because it goes on forever. All right, the range is greater than -3. So, therefore, basically, on the y-axis, which is the range, it's all of the things that are north of -3, up of -3, okay? Hold on one second. All right, I'm back. Next, axis of symmetry. Well, it goes through -3, all right? It's the point, or the line, the invisible line, the real line that's actually there, that again, when you fold over the parabola, you get the same on both sides. Because again, parabolas are symmetrical. All right, so what happens if we don't have a bx or a c? Basically, we just have y equals ax to the second power. Well, it means that the graph will form a parabola, duh, it's to the second power, And the vertex will be at 0, 0. So as long as you don't have this stuff going on, you already know where the vertex is, all right? And its line of symmetry will be the y-axis. So if you already know that the axis, the vertex goes through 0, 0, you really don't even have to have to do the math for it, though I will in just a second. And it also means the axis of symmetry is the y-axis, which means you really only have to graph the points on one side of the y-axis. You could graph a bunch of points that are on the negative side, or you could do it on the positive side. I like to do it on the positive side just because there's a little less confusion. But let's go ahead and do this so that you can see that when we don't have the B or C, it's really easy if we know where the axis of symmetry is, because then we can just say, well, if one dot is 2 from the axis of symmetry on this side, the dot on the other side of the axis of symmetry should also be 2 units over. Okay, so let's go ahead and do some number crunching to prove this to you. So we have negative 2x to the second power, where x is 0, and that means we're going to have the point 0, 0. Alrighty, so then let's go ahead and graph that point. Bam, there it is. Alright, so let's now do x is 1. 1 to the second power is 1 times negative 2 is negative 2. So now we have the point 1, negative 2. Bam, there it is. Now we also have x is 2. So 2 to the second power times negative 2 is 2 to the 2 negative 8, which is the point right there. So then if I connect the dots as beautifully as I can also then figure out what the points are on the other side of the parabola based on how far each point is from the axis of symmetry. And the axis of symmetry, again, is the y-axis. All right? So, again, that might have been a little too fast for you guys. So let me back up. So again, I'm going to figure out that that orange dot is 1 unit from the right of the y-axis, which means it should be 1 unit from the left of the y-axis. That's still too fast. I'll just play it again, okay? And then again, the green dot is 3 units on the right, which means the units on the left should also be 3. So then I already know where the dots are, so I don't have to spend so much time doing this if I know for a fact that it's going to have an axis, a y-axis is my line of symmetry. I can do one side of it and then just know that the other side is equidistant from the y-axis, also known as my line of symmetry in this particular case, from the other dots. Okay, let's go ahead and move on. And again, axis of symmetry. And again, since my A was negative, it means that my parabola is going to open downward. All right, hold on another second. So, again, parabola equidistant from axis of symmetry. Sorry, Mr. Michaels walked in. It's been a day of, interruptions. Anyway, all right, so continuing to explore. Quadratic functions can be ordered from widest to narrowest, or vice versa, by the graph and by the coefficient of A. So, if the number in front of x squared is between a, either positive or negative, because remember, just a negative a means it's facing downward, a positive a means it's facing upward, but what the absolute value of a is will determine how wide or narrow the parabola is. So if the absolute value of a, again, either positive or negative, is between 0 and 1, so basically a fraction or a decimal that is between 0 and 1, because again, 1.5 is a decimal, but it is greater than 1, so it doesn't count, but like 1/2, 0.5, 1/4, 1/26, whatever it ends up being, that's going to be your widest parabola, all right? It's going to spread out, all right? Now, if you have the absolute value of 1 equaling 1, it's going to be in the middle, all right? And this can either be obviously -1 or +1. Again, the negative or positive tells you opening direction, not width. And then the absolute value of a, if it's greater than 1, is going to be your widest. And actually, or narrowest width. Okay, narrowest width. So again, bigger than 1 is going to be your narrowest. Okay, I'm back again. Sorry about that. All right, so if we are going to order these 3 equations from widest to narrowest, we're going to look at A. So, that was way too fast. Okay, so the very first one has a 1 in front of it, which means it's going to be the middle width. Okay? And then if we look at the next one, it has a fraction which is less than 1. and that's going to be the widest. And if we look at the next one, it has a 2, which is greater than 1, so it's going to be the narrowest. So if we're going from widest to narrowest, it's going to be the one in the middle, the one on the left, and then the one on the right. There you go, from widest to narrowest. All right, there we go. All right, so graphing all of this business. Now, graphing y equals ax squared plus c. The y-axis is still the axis of symmetry, but the c determines where to move the parabola either up or down. By graphing using a table of values, this will become very apparent. Now, I skipped that table of values for you because you've already seen it, but you still need to know how to do it. Don't rely too heavily on SciGraph Cal because you're still going to have to graph on your tests and quizzes by hand. So please, 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 please know how to use a table to graph. All right, so again, if you have a positive c, it's going to push the parabola up. So in the example here, the red line, which is x squared plus 2, the parabola actually starts at y2, 0, 2, right there, okay? So that is the vertex, all right? So the c actually determines where the vertex is on the y-axis. So if the c is negative 2, in the case of the blue line, which is x squared minus 2, the vertex is actually negative 2. Now again, this is where you don't have a b. This only works if you don't have a b. So make sure you pay attention to that and don't try to do something with a b that's similar to this when you have a b, okay? And again, having the negative x squared minus 3 just means it's a downward parabola starting at 0, negative 3. Okay, so again, it's these c's, the constants, something that's not being multiplied by x, just one number by itself that will tell you if you don't have a bx, where on the y-axis that your vertex is for your parabola. Okay, so second to last slide, I swear, or no, this is the last slide. Weird. Maybe it's not. I don't know. We'll figure this out. Okay, so quadratic function relates to gravity, which is totally cool, and I'm going to make you do some fun stuff with this. So, well, I don't know. I think it's fun, so you're just going to have to go with the flow. And the only thing is we have to ignore wind resistance. So we can't do this with a piece of paper. We got to do this with like a bouncy ball or a book or something. All right, but the equation for this is h equals negative 16t. T is time in seconds to the second power plus c, where c is the initial height of the object. So if you go outside and you start dropping some things that are, relatively dense, that don't have much wind resistance, you're going to be able to see this and graph these out if you were able to time them. All right, so just remember that things fall fast, and therefore we're using seconds. All right, t is in seconds. So suppose a squirrel is in a tree 24 feet above the ground. She drops an acorn. We're going to graph the function based on the gravity function above. And then, we need to describe the reasonable domain and range. Domain and range. Okay, so t is time. The formula is h is equal to, h is height in feet, by the way, negative 16t squared minus 24, because that's how high the acorn is from the ground when it starts to fall. And we need to figure out at what time the height of the acorn is. So at time 0, when we do the math, we're going to figure out that the acorn is exactly 24 feet above the ground, because the acorn hasn't started falling yet, because it's time 0. The squirrel is just about to push it over. Now, after half a second has gone by, guess what? This acorn is 20 feet above the ground. Actually, let's pause that and let's scoot back a little. All right, and you do the math. It's 0.5 to the second power times negative 16 plus 24, which gives you 20. All right, so that's 20 feet above the ground. Now, at 1 second, the acorn is 8 feet above the ground, and at 1.25 seconds, so this is just over 1 second, 1/1000, the acorn is actually negative 1 foot. Well, we're assuming that in this ignoring air resistance world, that the actual ground is not solid and that the acorn could actually continue to fall on forever. The thing is obviously is not going to fall on forever. Because if I actually graph these points, which is the y-intercept. By the way, the y-intercept is the point where time hasn't started yet, because my x-axis is time. X-axis, it's time. in seconds, right? And my y-axis is height in feet. All right, so at 0 time, the acorn is 24 feet above the ground. And by the way, since height is the y-axis, when y is 0, that's the ground. All right, and most things don't fall through the ground. They're not massive enough to do so. This acorn definitely isn't going to do it. It's going to basically just hit the ground. Now, of course, we don't take into account like inertia and the fact that it still wants to keep moving, so we don't care that this point that the acorn's going to bounce, but it's going to keep going down. And actually, I use SciGraphCal to make this graph, but we can put the points that I just mapped out using math right there onto here. So those are the points, so that when I connect the dots, it's actually going to work out. All right? So obviously this acorn is falling straight down. The parabola is actually showing us the rate of the fall. All right? After half a second, right here, the acorn is 20 feet above the ground. So if we could like stop it and just like slow this acorn down and like take a picture of it and measure it, it's going to be at 20 feet after a 5-second fall. Now, 1 second. I thought I was going to sneeze. There it is. Okay. Now we could even do it again at 1/7 of a second. This acorn is 16 feet above the ground. And here's a good one. At a 1/9 of a second, the acorn is 11 feet above the ground. And at 1 whole second, as I've already figured out, it's 8 feet above the ground. And then it gets infinitely small. So we know that basically at about, what was that, 0.22 maybe seconds? Or no, 1.22 seconds, relatively, is when the acorn's going to hit the ground. Okay? All right, and again, the domain is the x range, and since we don't care about negative time for this particular problem, it's 0 to here for the domain, and for the range of the function, well, it's going to be 0 feet to 24 feet, because that's the point at which the acorn hit the ground. All right, guys, this is the longest video yet. So sorry. Break it up if you need to. Rewatch it if you need to. Parabolas are kind of scary, and I understand. All right, bye, guys.